back. Let's see this problem. It simply says that you are given the root of a binary search tree. Now they have defined what a binary search tree is. A binary search tree is in which for any node at any point of time, its left child is lesser than him, its right child is more than him. For example, as you can see, take any random node in this. Take any random node. Let's say I took a 6. Its left child, which is 5, is lesser than him. Its right child, which is 7, is more than him. Take any node. Let's say I took a number 1. Its left child 0, less, right child 2, more. Now for this binary search tree, what you have to do is you have to convert this to a greater tree. And what they are saying as a greater tree is such that the key of the original BST, and the key is this value, this is the key for it, it should be changed to the original key plus the sum of all the keys greater than the original key in the BST. Now, as you know, it is a binary search tree. Your prime task is for this node 4, all the values which are more than 4, which means 6, 5, 7, 8, if I take the summation of them, whatsoever summation will come out to be, I should add that in my 4, as in like I should add 26, because 5 plus 6 plus 7 plus 8 is 26, and this summation is now the new updated value of the BST. Cool. You have to repeat it for all the nodes. Now, one very basic brute force way is, for every node, go to the entire tree, check what all nodes are higher than this current node from where you started, take the summation, add that on your current node, and then update your tree value. So what you did, for every node you went on to the entire tree. So same you have to repeat for all the other nodes and go to the entire tree. So for one node, entire tree traversal O of n time. Again, if you don't know tree traversal, please go and watch the above video. Now that tree traversal can be again a simple in-order traversal or simple pure traversal. Any traversal will work. You just have to go to all the nodes roughly and ultimately find the answer. Now, because of this case, what will happen? You will repeat this for all the nodes. So it will be O of n square. So interviewer will now ask you to improvise it. To improvise it, you know that the above approach which you saw earlier, which is the n square approach, it will work for all the trees, any form of tree. But you have a catch. This is not a normal tree. This is a binary search tree, which means I very obviously know that if I have this node, all the nodes which are greater than him will always be to the right of him. So I will have to just take the summation of all these nodes which are on the right of him, add that summation onto my current node. Now, for some of you, you might start thinking, Aryan, it seems like that I will take the summation from the right and add to my current node. So it is not only the summation from the right subtree, because you might end up thinking, Aryan, it is a summation from the right subtree, and I might end up adding to my node, and that will give me the answer. Bro, it is much more than summation from the right subtree, because for this node, the right subtree is this, but the summation which I have to take is from the right portion of the tree. So it is very obvious that you might have felt that I will, Aryan, simply traverse my entire tree. I can use any traversal. Let's say I start from the node. Again, let's write a bit clean code, tree node star node. Then in this code, we know a simple base case always is, if the node is equals to null, then I should have to simply return. Now, as you can see, I'm returning directly. I'm not returning a specific value, because I know from a specific portion of the tree, I should not return a value. I will have to maintain a global right sum. What is the right sum so far? And this also gives me a hint that I have to firstly traverse on the right, maintain a global right sum. And again, why not a local sum? Why not a subtree sum? Because a subtree sum will not work. I have to maintain a global right sum and then go to my left. So I realized I have to not return it. I have to maintain a global right sum. Let's name it as GRS. This is global right sum. Then firstly, I have to make sure I have to go to my right. So I will go to my right. Let's say nodes right. Then as I go to my right, I know, okay, I am at the right node. Now for that right node, let's say I am at this node 8. I cannot go right much further because then it will done from here itself, which means I am standing at 8. If I'm standing at 8, my first task is that I should update my global sum with the current value, which is 8. And initially the global sum is initialized to 0. So I'll update that value to my global sum. Now my global sum has become 8. In that case, I should reassign that global sum current value to my node 8. So I'll say that node value should be equal to my global sum. Now when this is done, okay, I have assigned the new value of my global sum to my node. I should try for my left. Okay, I'll go and try for my left. So I'll simply go and try for my left. And then I will simply recursion will handle the entire stuff. Now, what will happen in the next step? Next step, for sure, there is no right. So there is no left. So it will go up to the parent, which means 7 called the right. So 7 right portion is done. So it will be landing here at this point, global sum. I will firstly add in my global sum the value 7. I'll receive the value 15. I should assign that. It will become 15. Then I'll go try for the left. There's no left. Again, it will go back to the parent. Again, for 6, right portion is done. It will add the node value, which means 6 added to a global sum 6. It will become a 21. Assign that 21 to a node value, which is 6. I assign that and then go to my left. I'll go to my left. If I go to my left, I know one thing for sure. I'm going to my left. Oh, this node is not yet done. Okay, go to its right. Go to its right. Oh, there is no right of node 5. Okay, go to its again. If there's no right, make sure add in the global sum value 5. Value 5 added. It becomes 26. Update that value. I update that value, which becomes 26. Now go to left. There is no left. Okay, go back. I'll go back. Okay, now this portion was done, so it will go back up parent. Again, for the node 4, right portion was done. It will add the global value. It will add a 4. I'll simply add a in the existing value, which is 26 global sum last time. I'll add a 4. I'll get a 30 global sum. Update that global sum. Update that global sum, and then move to the left. Move to the left. So this is, you can easily see how I'm maintaining a global sum, which indicates global right sum for me. Global right sum for me, and thus I will simply solve it. And this is your exact code itself. Now I'll show you the code once again. This is the code. I have a global sum, and this is how I wrote the same exact same code. Time complexity for this, if it's a simple traversal, so it's O of n time. Space will also be O of n because of the recursive stack which will be used. Now, although I don't go to the iterative way of solving the same problem, but I never ask iterative version of it, but many of my friends have asked it in the interviews. So that's the reason I'm just telling it how to solve it by the iterative way. We will repeat the exact same code. It's just that now we have to replicate this solve function. How I'm going to my right, I have to replicate that entire process by using my stack. How I will do it? Simply, let's check. So I was actually pushing these nodes in my recursive stack. If you remember, a recursive stack would look like, I would have started from 4, then pushed my 6. Again, I'm going to the right first, then pushed my 7, then pushed my 8. So this is how my recursive stack would have worked. So for sure, I have to firstly monitor a stack. I have to take, let's initialize the stack, and let's say tree node star st. Now for that stack, I know one thing for sure, that you start from one node. Let's say I start from the root node. Start from the root node itself. This is the root node. In the very beginning, your stack will be empty, so you can just keep on repeating. Again, you have some node, so you can keep on trying. You have some node, so while you can just say while your node, you have your node, while your node is not equals to your null, you can simply keep on trying for stuff. Okay, is it sufficient? Maybe. Let's see. Now what I can do is, if I have the node, I can go to its right. Firstly, if I have a node, I can push that to my stack, and then I can try for the right node. So I will simply say that if I have the node, which means while the node is not equals to null. Again, Aryan might say, Aryan, why these two things required? This first thing is okay. I have a node. This thing is I'm trying for the right portion of the node. But Aryan, then why not just if loop, like if condition? You will see that. Just take a second. Although you could have put if condition, and then coming back again, we could have changed it to while, but let's keep it while, because we know that we have to try for entire node. If we think this while is redundant, we can break it in the while loop also. Now, while the node is not equal to null, I should make one thing sure, that I should push that node onto my stack. Okay, I'll push that node onto my stack, which means I'll push that node, which means 4 is pushed. But 4 pushing is not sufficient. I have to go to right and then check if that is null, that is not null, push that also to my stack. So technically I'm going to my right and I say node is equals to nodes right. Now, okay, I went to the right. Okay, so what will happen with this while loop is you will push 6 also, then go to the right, you push 7 also, then go to the right, you push 8 also. Now ultimately you have your stack looking like this. This is your stack ST. Now what? Simply, your stack looks like this. What do I have to do? Remove the topmost element from the stack. So I'll simply remove it. So the node will now become my stack.top. Now when this is removed, I have to make sure that this is to be removed also. So stack.pop also. Now again, same stuff. Right portion is done. Your next task is global sum, assign the nodes value, like add in the nodes value, and then assign the global sum to the node, to the nodes value. Same step. I will say that global sum, assign that and add my nodes value, and then in my, again for the nodes value, assign that to my global sum value to the node value. Now the task was to go to your left. Technically it makes sense that you have to again use a while loop to go to the left, although you can use that and make another while loop while your node is not equal to null, all that stuff, but node is already processed. You just have to process the nodes left. So if I would have just said node should be equals to my nodes, again there are multiple ways to solve it, I'm just showing you one possible way. I just went to my left node. Okay, left node. But then Aryan, with this you said that your node was pointing to your 8. 8's left is null. If it is null, which means your node is now null, which means this will break here. Oh yes, exactly, it will break here. So technically what I should make sure is I have something in my stack. So while my stack is not empty, I can still try stuff. Okay, if I can try stuff, I will try stuff, which means stack is not empty, but node is null. Node is now pointing to null. Node, this is node right now because it was pointing to left. Stack is, it will not go here because node is not equal to null. It will come here. If it will come here, I will grab from the top of the stack. Okay, I'll grab my 7, and for sure I am at this point, grab my 7 again. Node is now pointing to 7 now. That's an interesting point. As you can see, node pointing to 7 now. Add the global sum. Add in my global sum, which was earlier 8, I added a 7, I got a 15. I assigned that to my node value, which is 7. I assigned that and I got a 15. Again, go to my nodes left. I'll go to node. Oh, node left is again a null. So now node again became a null. But this time it is 7's left, which is null. Again, come back. Again, the stack is not empty. Try back. Okay, try back. I will remove 6. I'll add 6 in my global sum. I'll get a 21. I'll assign to my value 21. Okay, and then go to my left. Node will become nodes left. 6 left is 5. So now node became a 5. Now node became a 5. If that's the case, I will come here back. Node became, again, remember, node became a 5. So this is not null. I'll push that to my stack. I'll push 5 onto my stack. Again, nodes left, it is, sorry, nodes right, it is null. I get out. I'll get the top. Top is 5. Add that to your sum, global sum, plus 5. Got a 26. Assign 26 to your 5. Okay. Now go to your left. Left is what? Left is null. So node is now again pointing to null. Okay. Again come back. But stack is not empty now. Okay. Remove. Okay. Not go here. Remove from the stack. Okay. Remove from the stack. 4 is removed. Add that to your global sum. Add plus 4. Got a 30. Now coming on back. This is done. Go to your left. I go to my left. Nodes left. Like, because node right now is set of which is 4. No, sorry. Node right now is 4. So 4's left is now 1. So now node will be 1. As you can see, 4's left is 1. So now node will be 1. If that's the case, my node will be 1. Again, repeat process. So you see, this one line can actually handle it was handled just because of I had this while loop, and this was handling, and thus you can repeat or can try for this iterative approach also. Now if you see the exact same code, it is written here itself, exact same code, exact same code, exact same code, or what I mentioned. Stack is not empty or node is not equal to null. Simply try for the while loop, go to the nodes right, then try for the same stuff as we saw in recursive, then go to the left portion of the node. See, this is much trickier to write than your recursive code. It's the reason it is asked in the interviews also. So again, for this, the time will be O of n space, because we're using a stack in this place, will be still O of n. Can you improvise it? Obviously we can, because we realize it's a simple traversal. Be more precise, it's a simple, again, you are going to the right, then node, then left. If I ask you, if you would have gone to the left, then node, then right, what traversal is this? It's a simple in order traversal. Now for the simple in order traversal, if a person asks you to optimize and give you the answer in, again, when I say optimize, you will have to go to all the nodes. So O of n time will always be taken, but the improvisation chance is in space. So I can improvise my space. In that case, if I want to improvise my space, which means I have to use some standard technique of improvising your tree traversal, and that is very standard and only one, which is Morris traversal. So whenever anyone asks you any traversal algorithm and asks you, after you write the recursive or the iterative code, and they ask you to optimize that code, you have to know Morris traversal. If you don't know it, you cannot do it in the interview. So Morris traversal, if you don't know what a Morris traversal is, please go and watch this video. Although I will try run here also, but please go and watch this video. It is very highly recommended. Again, this is the same video in which I taught traversals. Now a Morris traversal simply says that the actual issue which you were getting, because of which you were using a space, was you were keeping a track in a form of a stack, and that track or stack was needed just so that, okay, from 4 you go to 1, then you go to 0, then you have to come back to 1. That is the reason a recursive stack is needed or a iterative stack is needed. So what I will do, from 0, like from 4 then 1, I will make a thread to 1 to my parent. Again, how I will make it, I will tell you, but because of this thread, now I can reach to my 1. I don't have to keep track of my parent inside. Again, I don't have to keep track in a recursive stack. I just need one thread. That specific thread will keep a track of whom I have to go to. Then I go to my 1, then 2, then again a thread which will go to my parent, and then again right, then again 3. Again, this I'm showing a simple in order traversal, and then again I give a thread to go to my parent, again go, and again, as you can see, simply it's ended. But it was when you go from left, then node, as in then the root, as in node, and then the right. So this was your actual when you would have used it. But in our case, this is not how we are traversing. How we are traversing is, we are traversing from node, then we go to our right, then we go to our right, then ultimately I have to go to my parent, then I have to go to my parent, then I have to go to my parent. So ultimately, when again for 4, then 6, then 7, then 8, then 7, then 6, then 5, ultimately, because this is done, so I should go to my 4, then 1, then 2, then 3, then back to 2, then back to 1, then to 0. So for me, now the threads will be made like, okay, I go to here, then I go to here, right, again right, then make a thread to your parent. Again, make a thread to your parent. As you go to a 5, make a thread to your parent. Again, if you're confused, Aryan, why is this thread needed? Is it the big tree? Is it the big sufficient tree? What's the use case? If you're arguing on that part, just one video will solve all your doubts on arguing. But I'm just dry running just because of I want you guys to understand the reverse in order traversal. Then again, go to your left, right, root, and then again your left. So ultimately, what we realized is, for a specific node, I will have to go to its right. Then again, this is simple traversal, right? Morris traversal. then I'll go to its extreme left, then I would have gone back to the root. So this is, let's say, root. You went on to the root's right. In the, again, imagine this is the entire tree. Entire tree is there. In the existing Moorish traversal, which I taught in this video, I taught that if you have a node, you go to its left. From its left, this is the root node, this is the node. You go to its extreme right, then you build a thread to your root node. In this case, I have to iterate in the reverse order. So I will go to my just right. It is just right. Then I'll go to the entire left, entire deep down left. Then I will build back my thread from this node to my root node, or I can say my parent node from where I came in. And I have to repeat it for all the trees or all the subtrees, which means if I have a node like this, and if I build, let's say again, so what I have to do is that let's say this is my node, so its thread should point to my root, its thread, this specific thread should point to my root, this specific thread should point to my root, and so on and so forth. So that is how it should be done. Now if that is the case, you realize one basic thing, that you just have to change the code. Again, it's a simple exact same code as what we have seen in the Moorish traversal. What we will do now, again, in the very beginning, let's start writing the code itself, and parallelly we can also dry run on this specific example. Cool. Now what we will do, that we have our simple tree node star, which is, let's say, node. Now ideally, for sure, you will keep on doing until your node is not equals to your null. Then in that case, you have to firstly make sure that you have to try and go to its right, because ultimately that's what you are doing. You are trying for the right, then grabbing the global sum and stuff, then going to the left. But your Moorish traversal says that you have to go to the right, then go to its extreme left, build a thread, then you are good to traverse. You are good to traverse, which means you were here, you went on right, build the thread, now you can go to here, and then simply start traversing your tree again. Why I did and build this thread before going to node 6? Because ultimately when I'm at node 6, I would technically or automatically go to node 5. From node 5, I should have a path back to node 4. So it's the reason when I am at a node, I should make sure that for future purposes, I should make sure I should build the thread right now only, which should point to me. Any node which should point to me, I should build a thread right now only. So I did the same thing, that okay, this is when I can go to right. What if there is no right at all? Which means, what if there would have been no node here itself? If that would have been the case, I'll simply check if my nodes right, if this is equals to null, let's say null ptr or null null, then I know there's no right. So there's no right, simply apply again. If there's no right, apply your main crux. So I'll do one thing. In my global sum, I will add my nodes value. I will assign my nodes value to my global sum, and then I will go on to my left. That's what I would do. Okay, but this is when you did not have your right. But what if you had your right? If you had your right, then your task is that go to your right child. Let's name it as a right child, or you can say a post child, because if you remember, if this is the node for us, which we are saying, this is the pre node, this is the post node. So I'll go to my post node's extreme left. I should keep on going. When I have got that extreme left node, I should build a thread to my node itself. So I will say that I need this node. Let's name this node as post extreme left node. This is the name of this node, right? So I'll do the exact same stuff, that I will go and try to find my post extreme left node. Let's say I have written a post extreme left function, which will starting from this node, it will go and give me this post extreme left node. From this node, if you go and give me a post extreme node. Aryan, why have you written a function? Why you could have written here itself, right? The code itself. Yeah, I can write here itself. It's just like 2-3 liners. But let's write it separately so as that you understand it much clearly that what is happening in this function itself. So this function simply says I will return a node. So I have to return some node, and the function name is post extreme left function. And this will accept a node itself for me. Now, in that case, which means the node itself for me. In that case, what I will do, I will have to firstly make sure I have to get the post. So firstly, I'll get the post. Let's say I got the tree node star. I'll get the post. Post is my node's right. This is my post. Now my task was keep on going to the extreme left. So I'll simply have, where is it gone? Yeah. While my post left, or basically I can say post is node's right, and I know that I have my right. If it came here, which means node right is for sure here. So post is for sure here. So post left cannot be null. So while my post left is not equals to null, keep on going to your post left. Post will become post left. Ultimately, you will reach on to a point where the left is null. That's again, which means that it is post extreme left node. So I can simply return that post node also, post node itself, because this is now the extreme leftmost node. Again, this code is not correct right now. I'll do it, but this is what we have learned. This will perform the task and will make me reach my post extreme left node. When I have reached that post extreme left node, my prime task is that I should assign the thread, and I should say that post extreme left node's left thread should point to my node. So I should make sure I'll do this. But a quick question for you guys. Let's say you have made the thread, which means when you have made a thread, you will now shift your node here. Okay. Then let's say you did the entirety traversal, then let's say you shift and reach to your node while traversing left node, and then you come back to, let's say, your node, this node. If you go back to your right side, technically you should make sure two things. First thing is that you should not go right again. That's one thing. But if you would have seen that in the last video, I have told you that to handle this case, you can remove this thread entirely. You can remove this thread. There's no linkage at all. But in this case, you have to maintain the linkage. You have to maintain the tree structure, because you have to return that tree structure itself. So I have to maintain the linkage. In that case, I will go to my, again, same process. I'll go to my right, extreme left. If I see I have a linkage back to me, which means in the previous step, I build a thread. So I should remove the thread. And as I know, it was in the previous step I built a thread, which means I had already traversed it earlier. So this, because of finding a thread earlier, I realized I had already built my thread, which means I should not go on to my right again. I should rather go to my left. So that is the reason I told you that there's a possibility of you from your node going back to your right child again. That is again, there are two answers for it. One answer is remove that thread, which I taught you in this video. Other answer is because you have to maintain the structure. So make sure to come back here again. Now you see there's already a thread built back to you. So remove that thread and then proceed further. So it's a reason that there's a chance of you coming back again. So in this function, you have to make sure that while your left is not equal to null, or your left is not pointing, not pointing to that node. Sorry, it should be and should be not pointing to your node, root node. In that case, you can only go to your left. So this will, again, even if it is threaded, even if it is threaded or having a null, which means making a thread for the first time, still it will land onto this node, post extreme left. Now I'll simply have a check if this post extreme left nodes left, if this is equals, or if this is equals to null, which means I am here for the first time. If I'm here for the first time, my task is only one thing: build a thread. So I will simply build a thread and say post extreme left should be equal to my node. I build a simple thread. Now in that case, my thread is built, so I can now proceed with my node, and now my node can go to my right. Now my node, it will go to my right. Okay, and then it will simply repeat the process. So I can simply now go and easily, peacefully move my node to my right. Now when the node has gone to the right, okay, else it is done. But else cases, if it is pointing back, if it is again, because again it is pointing, it will go to the right, then I will do something for sure. It will again come again. I have to simply traverse the tree. It will again come back to my node. So node will again come back. It will try to again traverse. Again it sees, okay, the thread is already built. In this case, if the thread is already built, make sure to remove this thread. First thing is remove the thread, which means my post extreme left's node should now become equal to null. I have to remove this thread. After removing the thread, I know that I should now move to my left child, right? Because removing a thread means the thread was there previously, which means you built the thread in the previous step, which means you had already iterated on the right portion. So if you are here at this point, make sure that you have to go to left. But before going to the left, maqsad nahi bhulna, your main aim was to assign the global sum. So I know I am standing at the node itself. Before going to the left, I know I have to ultimately go to the left now. I have to go to the left now. But before going there, make sure to add in your global sum the node's value and also assign your node's value to your global sum. Cool. And ultimately this is your else case done. You remove the thread. Here you build the thread. Iterate on your right. Coming back, you remove the thread. Again, coming back again here at this point, you remove the thread. Got the sum, go to the left. And this is what you will do if you have your right. If not, then you will go to the left and repeat the same process. And this will keep on going until you have your node. So this is the while loop for us. Cool. This is your entire code which you have written. Cool. This is your entire code. As you can see, I'll show you quickly what you have written here. Let's see the code in a very proper formatted way. So as you can see, I have my node. I'll simply check if I have my right node or not. If you have your right node, if you don't have it, okay, assign global sum and go to your left. If you have a right node, okay, try to go and find your post extreme left node. If the thread is building for the first time, okay, build the thread, go to your right node. If the thread is already built, remove the thread. You have to go to your left. Before that, make sure to do your work and then go to your left. And this is your entire code. And again, because of this, time will be used as O of n. Now, why O of n as a time complexity? Please go and watch this one video in which I have dry run the entire model traversal very deeply and also explained it very deeply. Here I tried to dry run code by code, line by line, what will happen for this case. But space in this case will be O of 1 because of no recursive stack used. Cool. I hope you guys got it. Again, iterative, recursive, and Morris traversal. This is a very good question. Understanding, knowing it feels easy, but writing the code becomes very, very tricky. So you should know that what every step is doing of your code. Cool. Bye bye. Take care. See you. I hope you got it. If yes, then smash the like, baby. And yeah, see you. Goodbye. Take care. Discord join. Join the Discord server. Discord join.